In April of 2025, one of the most respected exoplanet research teams in the world stood in front of the scientific press and said something astronomers have been waiting decades to hear. They had found a molecule in the atmosphere of a distant planet that, as far as we know, is only ever produced by living organisms. The planet sits in the habitable zone of its star, 124 light years away, and the team behind the discovery called it the strongest evidence yet that life might exist somewhere beyond our own solar system. That announcement went everywhere. It should have. But here's what almost none of the follow-up coverage actually told you afterward. Because in the months since that announcement, a growing number of independent research teams have gone back through the exact same data. And what they've found has significantly changed the story. This is the real, complete timeline of what James Webb actually detected on a planet called K2-18b, what the original team claimed, why so many other scientists pushed back hard, and where the science genuinely stands right now, as of this year. If you want the full picture, instead of just the exciting headline, subscribe now, because this story isn't over, and understanding exactly where it stands matters. It also helps to understand exactly how Webb manages to study the atmosphere of a planet sitting more than 100 light years away in the first place, because the actual method involved is worth appreciating on its own. K2-18b, like most planets studied this way, was originally found and continues to be observed using something called the transit method. From Earth's perspective, the planet periodically passes directly in front of its star as it orbits, causing a tiny, precisely measurable dip in the star's overall brightness. Webb takes that same basic transit event and extracts something far more detailed from it. As starlight passes through the thin ring of atmosphere surrounding the planet's edge during a transit, specific wavelengths of that light get absorbed by whatever molecules happen to be present in the atmosphere, leaving a kind of chemical fingerprint embedded in the starlight that eventually reaches Webb's instruments. By carefully measuring exactly which wavelengths are missing or dimmed compared to the star's normal light, researchers can work backward to identify which specific molecules are present and roughly how abundant each one is. It's an extraordinarily indirect measurement, reading a chemical signature encoded in starlight that's traveled over 100 light years, filtered briefly through an atmosphere thousands of miles away from the planet's actual surface, which is part of why teasing apart one specific molecule, like dimethyl sulfide, from other molecules that absorb light at similar wavelengths, turns out to be such a genuinely difficult technical problem. Let's start with the planet itself, because K2-18b has been a genuinely interesting target for exoplanet researchers for years, well before any of this controversy began. It orbits a small, cool red dwarf star called K2-18, sitting in the constellation Leo, roughly 124 light years from Earth. The planet itself is considerably larger than Earth, with a radius a little over twice our own planet's, placing it in a category astronomers call a sub-Neptune, a size class that has no direct equivalent anywhere in our own solar system. What made K2-18b interesting in the first place is that it orbits squarely within its star's habitable zone, the range of distance from a star where temperatures could theoretically allow liquid water to exist on a planet's surface. The High hypothesis itself, separate from the specific DMS controversy, has also faced serious scientific pushback worth understanding honestly. Several independent research groups have published modeling work arguing that K2-18b's deep interior might not actually support a stable liquid water ocean the way the High concept requires. Under the intense pressure that would exist deep beneath a thick hydrogen atmosphere on a planet this size, some researchers have proposed the interior could instead be dominated by an extremely hot, high-pressure magma ocean, rather than anything resembling a habitable liquid water sea, a fundamentally different and considerably less hospitable environment. Other researchers have raised questions about whether a planet this size, generally referred to as a sub-Neptune or mini-Neptune, is even likely to retain a thin enough hydrogen atmosphere over billions of years for a genuine ocean atmosphere boundary to persist at all, rather than gradually evolving into something closer to a smaller, cooler version of Neptune itself. None of this rules out the High-Sean interpretation entirely, and Madhusudan's team has published responses defending the concept's plausibility, given the currently available data. But it's an important reminder that even the underlying planetary model this entire story depends on, separate from the specific biosignature debate, remains a genuinely open and actively contested question within the field. Back in 2023, a research team led by Niku Madhusudan, an astrophysicist at the University of Cambridge, used Webb to study K2-18b's atmosphere directly, and the results were already promising on their own. They confirmed the presence of methane and carbon dioxide in the planet's atmosphere, and notably did not detect ammonia, a gas that would typically be expected if the planet had a deep, gas-dominated interior similar to Neptune. Based on that combination, Madhusudan's team proposed that K2-18b might belong to a theoretical category of planet they call a Hycean world, a term combining the words hydrogen and ocean, describing a planet with a thick, hydrogen-rich atmosphere sitting above a genuine global ocean of liquid water. That 2023 paper also included something else, a weak, low-confidence hint of a molecule called dimethyl sulfide, often abbreviated as DMS, sitting in the data. On Earth, dimethyl sulfide is produced almost exclusively by marine life, primarily phytoplankton in our oceans. The 2023 signal was far too faint to draw any real conclusions from, but it was enough to make the team want to look again with better instruments. If a story built on tracking real science as it actually develops, rather than freezing on the most exciting headline, is the kind of thing you want more of, drop a like on this video right now. It genuinely helps this content reach more people who'd get value out of it. It's worth acknowledging directly why the April 2025 announcement spread as fast and as widely as it did, because that's part of this story too. Headlines around the world compressed a carefully hedged 3 sigma scientific result into phrases like strongest evidence yet for alien life. And in fairness to the outlets involved, that phrase did come directly from members of the research team themselves during the initial announcement. But a lot of the coverage that followed stripped away the surrounding context almost entirely. The statistical caveats, the explicit acknowledgement that 5 sigma confirmation was still needed, the plain fact that even a confirmed detection of DMS wouldn't automatically prove a biological origin. What most people who encountered this story actually saw was a single, simplified takeaway, that scientists had essentially found aliens, and that compressed version is exactly the kind of claim that then needs walking back once the more careful technical scientific process actually plays out over the following months. Understanding that gap between what actual working scientists claimed and how that claim traveled once it left their hands is arguably just as important as understanding the chemistry itself. That follow-up came on April 17, 2025, and this time the signal was considerably stronger. Using Webb's mid-infrared instrument to gather new data across a different portion of the light spectrum than the original 2023 observations, Madhusudan's team reported detecting spectral features consistent with dimethyl sulfide, and possibly a related compound called dimethyl disulfide, at a statistical confidence level described as 3 sigma. If the detection were real, the team calculated that these gases would need to be present at concentrations thousands of times higher than anything found in Earth's atmosphere, roughly 10 parts per million, compared to less than 1 part per billion here at home. Madhusudan described the scenario that best fit all the accumulated data as a Hycean world with an ocean genuinely teeming with life, and the team characterized the result as the strongest evidence yet that a planet beyond our solar system might host biological activity. It's important to actually understand what a 3 sigma confidence level means, because this is exactly where a lot of the public conversation around this discovery went off the rails. In statistics, sigma is a measure of how unlikely it would be to see a given signal purely by random chance, if there were actually nothing there at all. A 3 sigma result means there's roughly a 0.3% chance the detected pattern is just random noise in the data, which sounds fairly convincing on its own, but physicists have a much higher bar for anything they're willing to formally call a confirmed discovery, a 5 sigma threshold, corresponding to odds of roughly 1 in a few million, that the result is a statistical fluke. 3 sigma results in physics and astronomy get published, get discussed, and absolutely get taken seriously as worth investigating further. They do not, on their own, meet the standard required to say a discovery has been confirmed. Madhusudan's own team was upfront about this distinction at the time, explicitly framing the result as tantalizing and worth pursuing, rather than as a settled conclusion. If you found this level of nuance more interesting than the original headline, drop a comment and let me know. It genuinely helps me figure out what to cover next. And pursue it further, other scientists absolutely did, because a claim this significant was always going to draw intense scrutiny from the broader research community, exactly the way science is supposed to work. Just months after the April 2025 announcement, a team of researchers led by Michael Zhang at the University of Chicago published an independent reanalysis of the same underlying data and reached a considerably more cautious conclusion. Their central argument was that the specific spectral signature attributed to dimethyl sulfide sits in a region of the infrared spectrum where several other, far more mundane molecules, including simple hydrocarbons like ethane, produce very similar signals. Distinguishing DMS specifically from other plausible candidates, they argued, was genuinely difficult with the data currently available, and the original detection had relied heavily on a single observation pass, while combining multiple observation passes together produced a noticeably less convincing case. Their guiding principle, as one of the study's co-authors put it directly, was that scientists should always favor the simplest available explanation first, And ethane, a molecule already confirmed to exist on planets and moons throughout our own solar system, qualified as a simpler explanation than an unprecedented alien biosignature. That wasn't an isolated challenge either. Around the same period, a separate reanalysis effort led by Luis Wellbanks at Arizona State University dug back into the original 2023 dataset that had first hinted at DMS and reached an even more direct conclusion, describing the original tentative signal as essentially a false alarm once properly reanalyzed with a broader, less restrictive set of possible molecules included in the modeling. Their critique focused on a specific technical issue with how the original detection had been calculated, arguing that the analysis had used an artificially narrow list of candidate molecules to compare the data against, which can make a borderline signal appear to favor one specific interpretation, DMS in this case, simply because the alternative explanations were never given a fair chance to compete against it in the model. Perhaps most significantly, NASA itself weighed in through an independent study of its own. A NASA-led analysis, made public in July of 2025, worked through the full combined dataset, all three separate observation modes Webb had used to study K2-18b's atmosphere over time. And while the study did confirm the planet genuinely has a water-rich, complex atmosphere, it found no conclusive evidence for dimethyl sulfide at all, tempering the earlier excitement considerably. Even more recent reanalysis work, published in the opening weeks of this year and continuing through the first several months of 2026, examining the complete combined dataset across all of Webb's relevant instruments together, has continued to reach similar conclusions, finding the evidence for both dimethyl sulfide and dimethyl disulfide on K2-18b insufficient to support the original claim once the full body of available data is considered together rather than any single observation in isolation. It's also worth placing K2-18b in the broader context of what else Webb has been doing with its exoplanet observing time, because this isn't the telescope's only attempt at studying potentially habitable worlds. Webb has spent considerable observing time on the TRAPPIST-1 system, a compact family of 7 roughly Earth-sized rocky planets orbiting a small red dwarf star about 39 light-years away, with several of those planets sitting within their star's habitable zone. Those observations have produced their own steady stream of atmospheric measurements, detecting things like carbon dioxide on some of the inner planets, while finding hints that some of the outer cooler planets in that system may have thin atmospheres, or in some cases potentially none at all, results that continue to refine scientists' understanding of which kinds of planets around small, cool stars are actually capable of holding onto a meaningful atmosphere in the first place. None of the TRAPPIST-1 planets have produced anything resembling the DMS controversy surrounding K2-18b, but the ongoing work there matters because it's steadily building up the broader statistical picture scientists need, examining atmospheres across dozens of planets rather than treating any single dramatic result in isolation. That broader context is part of why the scientific community treated the K2-18b claim with exactly the kind of caution it received, because researchers studying these systems know from direct experience just how easily a single observation, however exciting, can turn out differently once more data comes in. So where does that actually leave things, honestly, as of right now? The methane and carbon dioxide detections from the original 2023 observations remain solid, confirmed at high statistical confidence, and not seriously disputed by any of the follow-up work. K2-18b's classification as a strong candidate for a Hycean world, a planet potentially covered by a genuine global ocean beneath a hydrogen-rich atmosphere, also remains a live and genuinely interesting hypothesis among researchers, even though that interpretation itself has faced its own separate scientific challenges regarding whether the planet's interior conditions would actually support a stable liquid water ocean rather than something more like a deep magma layer. What is not held up under continued scrutiny is the specific claim that traces a definitive biosignature gas in K2-18b's atmosphere. As it currently stands, the responsible accurate summary is that Madhusudan's team detected a real, statistically notable signal in the data, proposed and genuinely exciting interpretation of what that signal might mean, and multiple independent teams, using different analytical approaches on the same underlying observations, have since found that signal considerably less convincing than it first appeared, with some concluding it may not represent DMS at all. It's worth being clear about something important here, because this entire back and forth is not actually a story about science failing or a discovery being debunked in some embarrassing way. It's a story about science working exactly the way it's supposed to. A research team gathered genuinely new cutting-edge data, proposed their best interpretation of what it showed, published it transparently with an honestly reported confidence level well short of a formal discovery, and then the broader scientific community did precisely what it exists to do, testing that claim rigorously from multiple independent angles before anyone treats it as settled. Madhusudan and his team have never claimed to have definitively found alien life, and they've been consistently clear that additional observations were needed from the very beginning. What's happened since is that those additional observations and reanalyses of the existing ones have so far pointed toward a more cautious conclusion than the original headline suggested, and that's a normal, healthy part of how genuine scientific consensus eventually gets built. None of this means the search on K218b is finished either. Webb is expected to continue gathering additional data on this specific planet, and researchers on multiple sides of this debate have been explicit that more observations, ideally using different combinations of Webb's instruments and covering additional wavelength ranges, are exactly what's needed to finally settle the question one way or the other. Madhusudan's team has also said they intend to investigate whether dimethyl sulfide and dimethyl disulfide could plausibly be produced through purely non-biological chemical processes, at the concentrations being discussed, an important question to answer regardless of whether the original detection ultimately holds up, since even a confirmed detection of these molecules wouldn't automatically prove a biological origin unless non-living explanations could be reasonably ruled out first. So what does all of this actually add up to? James Webb did detect something genuinely interesting in the atmosphere of a planet sitting in its star's habitable zone, a planet that remains a serious candidate for hosting a global liquid water ocean beneath a thick hydrogen atmosphere. What it has not done, at least not yet, based on where the evidence currently stands after extensive independent scrutiny, is confirm the presence of a genuine biosignature gas, let alone actual life. The full honest version of this story is less immediately dramatic than the original April 2025 headline, but it's also a far better demonstration of how real science actually functions. Messy, self-correcting, and built on the assumption that even genuinely exciting results deserve to be checked, challenged, and checked again before anyone treats them as settled fact. There's a broader lesson in this specific saga that extends well beyond K218b itself, and it's worth sitting with before we close this one out. The search for life beyond Earth is going to keep producing moments exactly like this one. Tantalizing, statistically borderline signals that generate enormous public excitement long before the scientific community has had time to actually test them properly. That's not a flaw in how this kind of research works. It's an inherent feature of studying objects 100 light years away using light that's been stretched, filtered, and faintly altered across an almost incomprehensible distance before it ever reaches a telescope's mirror. The responsible way to follow stories like this isn't to treat the first exciting headline as final, and it isn't to dismiss every tentative claim as hype either. It's to actually follow the story as it unfolds, through the announcement, through the scrutiny, through the reanalysis, all the way to wherever the evidence actually settles, however long that takes. If stories like this, the complete and honest version rather than just the headline that got the most clicks, are what you come here for, subscribe to this channel and turn on notifications, because K218b is still being studied and there's a real chance new data settles this question in one direction or the other before too long. Thanks for watching, and I'll see you in the next one.